Now that we have our equilibrium equations, three of them, one for each degree of freedom, one for theta b, one for theta c, and one for the chord rotation term, we can then substitute in with our slope deflection expressions like so. There's your first term MBA, there's your second term MBC. For later shorthand work, I'm going to get tired of writing EK theta b every single time, so I'm going to do a little shorthand work here and then simplify this down progressively as we go. There's your fixed end moment term coming across, and then aggregate all the terms so that our equation 1 turns out to be this particular one here. And it's just easier to work with and when you write it in this kind of form. Do the same thing with equation 2. No new surprises. You just got to be careful and plot along as you substitute in so that you don't make mistakes. There are a couple of ways to check to see if you got mistakes, and they're revealed a little bit more easily in the matrix form that I'll show you at the here at the end of this step. And then you get the real long one, that is equation 3, because it has 4 member end moments in there. It's not equal to 0. It has a term out at the right. So I've organized the work a little bit differently. There's MAB. I separated out the terms, anticipating that I'll eventually get a theta C term in here as well. So there's your first one, then there's your second one, MBA. Here's your MCD term, and then your MDC term. It's supposed to all equal 100. So then I just add it all up together, simplify it down progressively, continue to move forward in simplifying it down, and then so there's your 4.5b plus 4.5c minus 18p equals 100. Now for kicks, I've gone ahead and double deck, because if I'm going to do this by hand, I like to have integer values of the constants if I can get them, and I can see that I easily could do that, so I have done that. It doesn't change anything in the linear algebra at all, right? I can multiply the whole thing by whatever I want to. Now, because I did that, I went back to the other equations and did the same thing, cleared out the 4.5 in those, collected the terms, represented it in matrix form, and that's where you get this set up here. And I realize it's kind of a flip-floppy thing here, and it can be a little bit hard to keep track of. Doesn't matter, right? It's only if you're processing things by hand what you're doing with this kind of approach. But it made it easy to look at the overall form of what we've got. And on that last one, note I also took and multiplied it by -1. That was just so I could illustrate for you the symmetry of this, what turns out to be our stiffness matrix. There's our unknown displacement terms, EK theta B, EK theta C, and EK psi. And the thing you have to be really careful about when you do these techniques are to keep these terms in the right way, the right proportion, and keeping track of all the numbers. Right now, you could do this by hand. It's a 3x3. It's a little bit painful, but it's not too bad. I chose this time to use a manipulator such as Excel to do the matrix multiplication, and came up then with the solution for B, C, and P to be what you see over here on the right. The 1.296, a positive or a clockwise rotation of B. That actually makes a whole lot of sense given the gravity load that's there. And then that means the middle of the span, or the beam that is going downwards, causing a clockwise rotation at B, a counterclockwise rotation at C. And then we've got a chord rotation term. That means that we have a counterclockwise rotation of the two columns, and that means the beam is swaying to the left, which is exactly what we anticipated way back in step 1. Let's look at this matrix form in just a little bit more before we charge off further. And that is now in this form. I went back to the original way that we had written these, except for there needs to be a minus sign. There we go. Here we go. Minus sign on that 18 term. So let me get that in there. Yep, that's a minus sign. That's correct. Okay, so when you look at this form again, and the BCP form is down below, but here again emphasizing what we really have, and we've got the fixed end moments sitting here. that eventually then we can take to the other side. So they change signs, and you'll see in a lot of write-ups that when they write this in simple matrix form, stiffness matrix times the unknown vector of unknown displacements plus the fixed end forces effects equal then the actual nodal or joint forces, and then you can take those to the other side, do the symbolic inversion of K, and solve for your unknown displacements. They like to write it in this form, particularly when you get into the direct stiffness and the finite element method approach. Right? So that sort of concludes the part of what does the math solution look like. Now we're in the next step going to go back and back substitute in and do some final analysis.